We have introduced quantum mechanics through the Schrödinger equation and the spatial and temporal wave functions that are solutions to it. This is directly useful, for example, for many problems with electrons and simple oscillators. This discussion of Schrödinger's equation has also introduced a large number of the key concepts in quantum mechanics, such as quantum mechanical states and amplitudes, Born's rule for calculating the probability of outcomes from the modulus squared of quantum mechanical amplitudes, the ideas of eigenvalues and eigenfunctions, the concept of operators representing physical quantities, such as the Hamiltonian for energy and other operators such as those for momentum and position, the use of these operators for calculating expectation values, and the ideas of superpositions and the evolution of quantum mechanical systems in time. But quantum mechanics is much broader than this. And even those systems that can be handled with the Schrödinger equation that we've looked at so far are by no means all the systems we have to look at in the physics of quantum mechanics. For example, photons are not described by this kind of Schrödinger equation. We've not yet dealt with the spin attribute of electrons and other elementary particles. We've not introduced angular momentum, and we've not considered systems with more than one particle. To look at all of these things, we need a more general mathematical formalism to go much further. Now, the first piece of good news is that all these concepts we've been introducing and discussing for Schrödinger's equation remain central to quantum mechanics as we go forward. The second piece of good news is that the more general mathematical formalism we need is just linear algebra. If you're familiar with matrices, then you have the core of this formalism already. Of course, linear algebra is a topic that occurs in many different areas of science and mathematics. As I said, we find it in matrix algebra, but also in Fourier transforms, solutions of linear differential equations, solutions of integral equations, and analysis of linear systems in general. Here, as we go forward, we're going to assume that you are familiar with at least the matrix version of linear algebra. Let me emphasize here, the formalism of quantum mechanics is based on linear algebra because quantum mechanics is apparently absolutely linear in certain specific ways. Specifically, it's always linear in the quantum mechanical amplitude, which so far has mostly meant a spatial wave function amplitude. To generalize linear algebra for quantum mechanics, we introduce shorthand notations, especially what's called Dirac's bra-ket notation. That's really a pun on the word bracket. But the underlying concepts are standard for linear algebra. Indeed, the Dirac notation is actually one of the best notations to use for linear algebra generally. It's particularly intuitive when you use it, and we can even view it as suggesting for you the operations that you can perform. Our mathematical approach here is deliberately informal. The emphasis is on grasping the core concepts and on ways of visualizing the mathematical operations. Indeed, our major goals here will be to give you a way of visualizing quantum mechanics mathematically and to help develop an intuitive understanding of quantum mechanics that extends to a broad range of problems.